Alright everybody, today's lesson is 2-3 matrices, and you want to put this in your notebook and title your notebook this way. Matrices is the plural of the word matrix, and a matrix is, mathematically at least, is simply a collection of elements. Most of the times we put numbers in them, but not always. You can almost think of them as like cells of an Excel spreadsheet, where you're going to be putting numbers into those cells. They could be representing multiple different things. We'll see in a slide coming up where they could represent different types of quantities in manufacturing and keeping track of data. There is a field of mathematics right now called big data, where companies take all of their information and manipulate that information statistically, and a lot of times they're using matrices and arrays of numbers. So a couple definitions here. So a matrix is an array of elements with dimensions given in rows and columns. That's really important. So you want to jot that down. So we give dimensions of matrices. So the first matrix over here is a 2 by 2 matrix, meaning that there are 2 rows, again, rows go horizontally, and 2 columns. Columns go vertically, just like in Excel. So this next one, it has 2 rows and 5 columns, so it's a 2 by 5. And the last one has 3 rows, 3 rows, and 1 column, so that makes this one a 3 by 1 matrix. So super easy to kind of give the dimensions, and the dimensions are important because sometimes you can do things with them and sometimes you can't. So let's take a look. Again, as in all my videos, make sure that if I'm going too fast, pause it and rewind and go back again and maybe listen again. All right, so let's just take a look at how to take just a random set of data, which is all kind of jumbled up in an expression or a sentence here, and kind of try to organize it. So this is a theater that was selling tickets, and there was Autumn Sky was one movie, 423 adults, 135 students, Joe the Teenage Ape, and adult and student tickets, and Young Moses, adult and student tickets. So we want to use a matrix to represent the data. Now if you look carefully, there are 6 numbers here of data. So how am I going to arrange that? Well, I could do 2 rows and 3 columns, or 3 rows and 2 columns. So let's see what I can squeeze in here. I'm going to do 3 rows and 2 columns. My 2 columns are going to represent student and adult tickets, and my rows are going to be Autumn Sky, Joe the Teenage Ape, and Young Moses. So Autumn Sky, students, how many were there ticket sales? There was 135. How many adults? 423. Joe the Teenage Ape had 389 students, 413 adults, and Young Moses had 402 students and 472 adults. So nice, neat, and clean. So now this little matrix, which we use these little brackets on the side to enclose the numbers in the matrix, they will represent, and it's a nice, neat, and clean as opposed to all jumbled up there. All right, so how about, let's take a look at this next example down below. So now we have numbers and expressions in them. Now let's be careful. Let's look here. These are both a 2 by 1. There's 2 rows and 1 column. It happens to be a binomial, a 2-termed expression in there, but there are 2 rows and 1 column. Well, for matrices to be equal to each other, they have to have the same dimensions. 2 rows, 1 column equaling 2 rows, 1 column, which means that this element up top here, which is technically element 1, 1, first row, first column, must be equal to element 1, 1 in the other matrix. So I can say y plus 4 has to equal x minus 1. And element 2, 1, second row, first column, is going to be equal to element 2, 1. So y must be equal to 3x. And I want to know what y and x are. Well, from what we've done recently, system of equations, I'm going to use substitution. This one looks like a nice, easy substitution. 3x plus 4 equals x minus 1. So 2x equals negative 5. I get x is equal to negative 5 halves. And if x is equal to negative 5 halves, y, just multiplying by 3, equation that's above, must be negative 15 halves. And so therefore my solution, again, we like to write them in an ordered pair. Again, so kind of taking equations and putting them into a matrix so you can have another way of expressing them. All right. So what if I have two matrices? Matrix A, so matrix A is a 2 by 2, and matrix B is another 2 by 2. You might want to pause so you can copy those two down. And what I want to do is add these two matrices together. Now, in order to add or subtract matrices, they have to be the same dimension. So 2 by 2 equaling a 2 by 2. Well, that works. So you are literally going to take, to find the matrix that's the sum of those, you are going to take and add like elements in like positions. So element 1, 1, first row, first column is 3 in the first one and 5 in the second one. So I'm just going to do 3 plus 5. And I'll show my final matrix here. I'm just showing the operation. So that's going to be 8. The next one's going to be 0 plus 1. So that's element first row, second column, so 1, 2. So that's going to be 1. And negative 1 plus negative 3 for these down here. And that's negative 4. And element 5 and 4. And I get 9. Is it that easy, you said? Yup, it is that easy. And we could do the exact same thing for subtraction. So just term by term, one element adding it to another element. Addition and subtraction is a piece of cake. So now what happens in this expression down here? So you might want to pause the video here and copy this equation and these two new matrices down. So these are called scalars. And a scalar is just a number in front of a matrix that multiplies all the elements in the matrix by that number. So 2 is going to multiply by every element in matrix X. So I'm going to have 2 times the matrix 4, negative 3, negative 6, 0, minus 3 times matrix 9, 0, 27, negative 3. So I'm going to multiply everything through. So that's going to be 8, negative 12, negative 6, and 0. That's a 2. Minus, okay, 3 times 9 is 27. 3 times 27 is 81. 0 and negative 9. And I'm going to subtract them. All right, so you can subtract, or the other little trick that you can do here is that you can then turn this into addition and multiply by another scalar of negative 1. And then we'll just add these two together. So my final matrix, which will be another 2 by 2, so 8 plus negative 27, negative 19. Negative 12 minus 81, that's negative 93. Oops, pen's not working. Negative 6 plus 0 is negative 6, and 0 plus 9 is 9. There is my difference of these with scalars. Again, super easy operation to do. All right, now matrix multiplication gets a little bit tricky, and I'm going to take a look at this in a second video, so we're going to stop this one because I'm going to switch over to my graphing calculator because these we're going to do in our graphing calculator. Let's at least write down here first a couple things before we go, or switch over. For matrix multiplication, the number of columns in the first matrix must be equal to the number of rows in the second. So what does that mean? Well, this first matrix over here is a 2 by 3. 2 rows, 3 columns. This matrix is 3 columns, 4 rows. 3 rows, 4 columns. Notice how the number of columns in the first matrix is equal to the number of rows in the second matrix. So I can multiply them together. Matrices don't have to be in the same dimensions to multiply. They can, but here's an example where they're not. So a 2 by 3 and a 3 by 4 can be multiplied together, and the resulting matrix is going to be a 2 by 4, the outer matrices dimensions. So what's going to happen, let me show you, and then we'll switch videos here. To find all the elements of this 2 by 4, so we're going to have 2 rows and 4 columns. Well, you're going to take this row times this column. That's why rows and columns is really important. So we're going to take 3 times 0 plus -8 times -4 plus 1 times 1. Add those all up and we're going to get that element. All right, I'm going to switch over to a piece of paper here and we'll do it on that one.